Okay, so this is 5.8 natural logs. So we talked about log 10s. Now we're going to talk about natural logs. So E, which is approximately 2.71828, right? It's the base for natural logs. So they don't really, everything that we do to natural logs is exactly the same as the other logs. All the laws of logarithms apply to that. So let's just go down and look at this one. So if you put E 2.4, plug it into your calculator, that's what you're going to get. Natural log of 4, plug it into your calculator, you're going to get that. Now, this is interesting. This question here, ln e to the 5. So if you rearrange this, the 5 is going to go to the front. So then you end up with 5 ln e. Well, here's the interesting thing is ln e, this thing right here, is actually equal to 1. So 5 times 1 is 5. So if you see ln e, that is just going to be replaced with 1. So example 2, let's solve one of these things. So you know you have to use natural logs right away because of the e. So what we do is we natural log both sides, ln and ln. Rules are all the same. This 2 minus x comes to the front, right? It's the exponent that comes to the front. What did we just say about ln e? It's 1. So 2 minus x times 1 is just 2 minus x. So 2 minus x equals ln 7. We want to isolate x by itself, so bring over, well, a bunch of ways to do this. You can move the x over here and the ln 7 over here. It doesn't matter. You end up with your x, so then you do 2 minus ln of 7, you get your answer. So it's really quite simple. Okay, so let's go and look at where this stuff comes into real quality. Stuff is radioactive decay, and I think the next example of that is investments. This is where you'll see natural logs all the time. So what we got is when a quantity is continually increasing or decreasing, it has either growth or decay that's modeled by A equals PERT, right? A is the final amount, P is the initial amount, E is obviously natural logs there, R is the rate, and T is the time. Okay, so what we got is the half-life of radioactive technetium is 14 days, and you currently have 2 kilograms of it. So what we do is we want to find the formula for the substance. So let's look down here. So we use A equals PERT. And what we can do is we have currently, right, 2 kilograms and half-life. Well, think about that for a minute. If we have 2 kilograms now, how much would it be when it's half of it? Well, that'd be 1. Oh, that's not that hard to figure out. R is the rate, and we don't know yet, and days is 14 days. Okay, so let's do the math. How do we get rid of this 2? We divide by 2. So we end up with 1/2 equals E 14R. Wow, we can't solve that, but here's what we can do. We can natural log both sides. So if we natural log both sides, put an ln in front of this one and an L in front of this one. Okay, we can do the math then. Well, ln of a half equals ln E 14R. Well, what do we do with this 14R? It's an exponent, so you bring it to the front, right? The laws of logs. Okay. Oh, ln E. Look at that. What is that again? That's 1. Oh, nice. It actually balances itself out really easily. So ln a half equals 14R. How do we get R by itself? We divide both sides by 14. So we do this. We end up dividing by 14. Oh, that's weird. It's a negative rate. Why is it a negative rate? Well, it's reducing, right? It's going down. It's decaying. Okay, so now what we can do is we can answer the next question. How much will be left after 20 days? So A, we're looking for A now. Why do we start with 2? Right? Because we currently have 2 kilograms of it. Right? E is whatever it is. Where'd this number come from? Well, that's the rate that we just calculated. And T is time in 20. So we can just do the math. A equals 2E, all of this. We find out, okay, after 20 days, we're going to have 0.743 kilograms. Now, if you think about that, that actually makes sense. If the half-life was 14 days, this is more than the half-life, so we should end up with less than 1 kilogram. Okay, example number 4 here. How long will it take an investment at 7.25% compounded annually to double or to triple? So let the investment be N dollars, because we're not dealing with amounts here, right? They didn't give us amount. We just have to use variables here. And how long would it be when it doubles? Well, that's easy. That would be 2N. Hey, what would it be if it triples? That would be 3N. So here's that formula. We've seen that before in one of the earlier lessons. This is the compound interest formula. So 2N equals N, right? Because we don't know how much we start with, but we know it's going to be to double. 1 plus the rate. There's the rate as a decimal. N is 1 because it's compounded annually. There's the 1 there. And T is what we're looking for. We don't know the time. So we can deal with this. Well, how do you get rid of the N in this case? We can divide both sides by N. That's easy. That would just get your numbers down. Oh, okay. And then you take this divided by 1 plus this. Oh, that's easy. That's just 1.0725, all raised to the T, because 1 times T is T. Well, look at this. That's simplified down really, really easy. Okay. Can't solve that. They're different bases. So what we can do is we can natural log both sides. So ln2, ln all of this. Okay. What do we do with the T? It's an exponent, so we bring it down the front. The key is you got to get the variable by itself. So how do we get rid of this ln of 1.0725? Well, you divide both sides by that. So you have ln2 divided by that. Comes out to 9.9 years. Oh. Now the question asks then, okay, what would it take to triple? Like right here, triple. Well, you don't have to do all the work again. The only thing that changes is this thing right here. This 2 that's right here will now become a 3 if it's to triple. So then you can do ln of 3 divided by that, 15.7 years. So it works out really, really easy. So this allows you with natural logs to take any part of this compound interest formula and solve for it. You just got a natural log both sides. Okay, so that's 5.8 there.